Good afternoon, ladies and gentlemen. Welcome to Engineering Mathematics 2. And the topic this afternoon is infinite series and sequences. Infinite series and sequences. Yeah, so in the previous discussion, we looked at the application of Taylor's and Maclaurin's polynomials to approximate the expansions and values of various functions, which can be observed that the approximation often becomes more accurate as the degree of the polynomial increases. In order to master and develop a theory of infinite series, we begin by studying the closely related idea, which is that of infinite sequences. Infinite sequences. Okay. So we begin by looking at a sequence. What is a sequence? A sequence, by definition, is a succession of numbers that are arranged in a definite order. For instance, the sequence we have here, 1, 3, 5, 7, 9, then dot, dot, dot. So the 3 dots at the end indicate that this series goes on and on and on. The sequence, rather. This sequence goes on and on and on infinitely. The individual numbers in a sequence are called terms of the sequence. And a sequence having only a finite number of terms, is called a finite sequence. Whereas one that involves an infinite number of terms is called an infinite sequence. So such a sequence can be indicated by, this is an example of an infinite sequence. So it starts from A1, A2, A3, then there are 3 dots indicating that there are several terms in between there. Then we have AN, the nth term. Then from the nth term, we continue with the 3 dots. 3 dots mean continuation. So since at the end there are 3 dots, it means this sequence is an infinite one. So the general term or the nth term in this case is denoted by AN, as we just mentioned. So in order to specify the sequence, it is sufficient to provide a rule or a formula for the nth term. So a sequence that converges to a limit, is known as a convergent sequence. A sequence that converges to a limit is known as a convergent sequence, while one that does not converge is known as a divergent sequence. Okay? All right. So let's look at the properties of limits of sequences. Let's look at the properties of limits of sequences. Suppose that the sequences AN and BN, these are 2 different sequences. Sequences AN and BN converge to limits A and B respectively. So the sequence AN converges to limit A and the sequence BN converges to limit B. And that there's a number C, which is a constant, then the following properties hold. So property number 1, the limit of C as n approaches infinity is equal to C. I think some of these rules we did them under limits in EGM 211. You realize that there isn't a big difference. So the limit of C, the constant C as n approaches infinity, is equal to C. Then the second one, the limit of CAN. So we have AN. AN is the sequence, the first sequence that converges to limit A, the one we just mentioned here. So this AN has got a coefficient constant, which is the C. So the limit of the product of the constant and the sequence as the value of n approaches infinity is the same as having the constant taken out. So if you take out the constant, you remain with the limit of an as n approaches infinity. So the final answer then becomes the product of the constant C and the limit A. Then we move to 3. So 3, supposing you have now two sequences adding, the limit of the sum of two sequences as n approaches infinity is just the same as adding two separate limits. So adding two separate limits, so which gives us A plus B. This is quite straightforward. Then we go to number 4. The limit as the limit when you have a difference of the sequence A and sequence B, the difference between these two sequences as the value of n approaches infinity is the same as subtracting the two limits, which is just the same as saying A minus B. Then we move to the fifth. For the fifth, it's about the product. So the product of the two sequences mentioned above, if you are to find the limit of the product of the two sequences as n approaches infinity, this is the same as multiplying the limits of the two sequences as the values of n approaches infinity, which is just the same as A times B. Then let's move to 6. So for 6, if Bn is not equal to 0, this is a very important condition. If the sequence Bn is not equal to 0 for all positive integers n, and if B is not equal to 0, then this limit holds. Then this limit holds. Okay. Yeah, so we are saying the condition Bn is not equal to 0 is very important because we cannot tolerate a mathematical abstract such as this one, A over 0. This is undefined. So for Bn not to be equal to 0, we are trying to avoid this situation. We're trying to avoid this situation. Okay, so let's move. Somebody wrote this. Why do you dent the screen again? So we move to 7. 7, the limit of C over n raised to the power k as n approaches infinity is equal to 0. This is provided k is a constant. This is also another very important property that we need to remember. Okay, then if A, the magnitude of A is less than 1, then the limit of a raised to the power n as n approaches infinity also approaches 0. It approaches 0. And if the magnitude of a is greater than 1, then the sequence, people are still joining in, then a raised to the power n, which is this value here, a raised to the power n, diverges. So this diverges when the magnitude of a is greater than 1. Okay. Yeah. So meanwhile, we know that the n here is approaching infinity. The n is approaching infinity, the one on the superscript part. Okay. So let's move now. As indicated, an indicated sum of all the terms of an infinite sequence, such as this one. This is a sum. This is the sum of the terms of an infinite sequence. Because what we were looking at previously was just terms being lined up one after the other. Now, the sum of the terms of an infinite sequence, such as A1 plus A2 plus A3 plus A4, and it goes on and on infinitely. Such a sum is known as an infinite series. So if you add up the terms of a sequence, you come up with a series. So if you add the terms of a finite sequence, you come up with a finite series. Okay, so this one here is called an infinite series, or simply a series. So using the sigma notation, we can write the series as, this is how we write it. So sigma an, where n ranges from 1 to infinity. You see, this is how this expression is simplified when you use the sigma notation. Then the sum Sn of the first n terms of the series, this same series, the first n terms of the series is called the nth partial sum of the series, because you cannot go on adding all the terms of an infinite series, but you go up to a certain term. Like in this case, you go up to the nth term. Okay, so if you find the sum of the first n terms of this sequence, then you are getting what you call the nth partial sum of the series, and that is illustrated on the next slide. So the sequence, people are still joining. The sequence Sn is referred to as the sequence of partial sums of the series. Notice that for each positive integer n, we have the sum n plus 1 is equal to sum n plus a, then subscript n plus 1. So you keep on adding just like this to get the sum of the first n terms. So you keep on adding, following this rule. This is a very, very simple rule to follow. Okay? Then, let's look at the convergence of an infinite series. You realize that there are a lot of theories in this topic. Yeah, but don't be intimidated. They are very easy to remember. If the sequence Sn of partial sums of the infinite series shown here, if it converges to a limit, S is equal to the limit of Sn as n approaches infinity, we say that the infinite series sigma ak as k ranges from 1 to infinity converges, and that its sum is S. You get the point? So if the sequence Sn of partial sums of the infinite series this value, which we already mentioned, if it converges to a limit such as it gives this one, if it converges to this limit, then we say that the infinite series converges and its sum is S. Straightforward statement. If the infinite series converges and its sum is S, we write it as this. So this is how we write it in the sigma notation. S is equal to sigma AK as K ranges from 1 to infinity. So an infinite series that does not converge is said to diverge. This is supposed to be diverge. An infinite series that does not converge is said to diverge. Diverge. Okay, so it's said to diverge. Okay, we move. Let's look at other properties. We have 8 minutes before we break. Properties of infinite series. If the series sigma AK as K ranges from 1 to infinity converges, then the limit AN as N approaches infinity is 0. So if the limit AN as N approaches infinity does not exist, or if it exists but is different from 0, then the series is said to be divergent. It's said to be divergent. Okay, let's move. It's all properties, if you've noticed. Let's now look at the linear properties in the last 7 minutes. Linear properties of series. Number 1, let sigma AN as n ranging from 1 to infinity be equal to A, and sigma Bn, where n ranges from 1 to infinity, is equal to B convergent series. So these two are convergent series. Then the following properties are valid. Okay, if these two are convergent, then the following properties are valid. So you've seen that these properties we've listed are similar to the ones we talked about under sequences. So this part, this one, and this one is similar, very similar to the properties we discussed under sequences. So if we go to number 2, if sigma AN is a convergent series and C is a constant, then sigma CAN is also convergent, and sigma CAN as with n ranging from 1 to infinity is equal to this. Have you seen? Even this property is similar to the property we discussed under sequences. So these things are very much related. Then if sigma AN, where n ranges from 1 to infinity, is a divergent series and C is a non-zero constant, then sigma CAN, when n ranges from 1 to infinity, is also divergent. This is very easy to understand. Since this is divergent, even if you have C, which is a non-zero constant, multiplying, the resultant will still be divergent. So if the series sigma AN, where n is from 1 to infinity, converges, and the series BN, sigma BN, where n ranges from 1 to infinity, diverges, then the series which is the sum of AN and BN, also diverges. Okay, this is straightforward. Let's look at the convergence of an infinite series. An infinite series converges to L if its partial sums Sn converge to L. That is, as n approaches infinity. So down here is an illustration. So we have sigma AN where n ranges from 1 to infinity, approaching L, if the limit of Sn as n approaches infinity is also equal to L. Okay? Then let's move. Let's look at other ways of testing for convergence. So there are several others, but we decided to select just those that we feel are important for engineers. So these are properties that are key in your engineering experience and the fraternity at all. So we look at the nth term test. If the series sigma an, where n ranges from 1 to infinity, converges, then the limit of an as n approaches infinity approaches 0 or is equal to 0. The convergence of the statement is false. Or the converse of the statement is not true. Okay? Then, sufficient condition for divergence. If the limit of an as n approaches infinity is not equal to 0, or if this limit does not exist at all, then the series an, sigma an, as n ranges from 1 to infinity, diverges. And all these properties, you realize that they are all interrelated, though they may have different names, but they are interrelated. Then let's look at the comparison test. Let sigma an and sigma bn be two infinite series such that an falls between 0 and bn for all values of n. Then the following comparison tests are valid. Number 1, if sigma bn is convergent, then sigma an is also convergent. Number 2, if sigma an is divergent, then sigma bn is also divergent. Straightforward. We have 1 minute left. Let's look at one. In 1 minute, I think we'll do these properties here. Let's look at the limit comparison test. Let sigma an and sigma bn be two infinite series such that an and bn are positive for all values of n. Then the following limit comparison tests are valid. Number 1, if the limit of the quotient of an and bn falls between 0 and infinity, then sigma an and sigma bn are both convergent or both divergent. Number 2, if the limit of the quotient of an and bn as n approaches infinity is equal to 0, then sigma bn is convergent, implies that series sigma an is also convergent. Then if the limit of an divided by bn as n approaches infinity or is equal to infinity, then sigma bn divergent implies that the series sigma an is also divergent. Okay, let me close for now and generate a new invite link. Okay, so we'll meet on the other side.